Welcome to the session on prestressed concrete sections. Now in this session we are going to solve the problem based on the prestressed concrete to find out the extreme stresses in the top and bottom fiber of the sections. So I am Professor Sri Krishna Gosavi from Walchand Institute of Technology, Solapur. I am working as assistant professor in civil engineering department. So today we are going to see the numericals which is on the prestressed concrete, and in this numerical we are going to solve this by using the stress concept as well as by using the strength concept. So both the methods we are going to apply over here. So the learning objective of this through this, the student will be able to analyze and find out the resultant stresses induced in the prestressed concrete beams by using both the concepts, that is the stress concept as well as the strain concept, and that we will now do it with the help of this problem. So now the given numerical is a prestressed concrete beam 400 by 600 mm in section has a span of 6 meter and is subjected to a UDL of 20 kilonewton per meter including the self weight. The prestressing tendons which are located along the longitudinal centroidal axis provides an effective prestressing force of 1200 kilonewton. Determine the extreme stresses at midspan by stress concept and strength concept. So now here in the given problem, if we write down the given data, then in the given what they have given, the size of section is given. Size is equal to, how much is the size? It is 400 by 600 mm. This is the size. Size is given. Then they have given prestressing force P. That force, it is 1200 kilonewton. So the prestressing force is 1200 kilonewton. Span of section is also known to us. So the span, that is L, it is given as 6 meter. So the span is 6 meter. Then here you can see the prestressing tendons which are located along the longitudinal centroidal axis provides an effective longitudinal centroidal axis. So it means that the eccentricity in this numerical is given as 0. It means that the provided tendons are concentric tendons and those are passing through the CG of the beam. There is 0 eccentricity. So here I have written E is equal to 0. So now first we will begin with the stress concept. So here in the stress concept method, so we will begin with this method. So here in the stress concept, first we will calculate the cross section, then we will calculate the Z section modulus, because the resultant stress in the stress concept, it can be calculated as resultant stress is equal to direct stress, that is P by A, then stress due to eccentricity, that is P by Z, and then stress due to bending, that is the external loading. Okay, so external loading, here you can see a UDL of 20 kilonewton per meter it is given. Here if you see here, the UDL of 20 kilonewton per meter is given. So now by using this stress concept, first cross-sectional area is equal to, so it is 400 by 600 which is equal to 24 into 10 raised to 6 mm square. This is the cross-sectional area. After this we will calculate the section modulus. So the section modulus is nothing but Z. We know that for rectangular section the section modulus is BD square by 6. So it can be calculated as 400 into 600 square by 6. So Z is equal to, the answer is 24 into 10 raised to 6 mm cube. So this is the value of Z. After the calculation of Z, we will calculate the bending moment due to external loading. So bending moment. So to calculate the bending moment M, the formula is WL square by 8. So it is WL square by 8. Bending moment is nothing but WL square by 8. Now here the given loading is 20. It is including of self weight. So there is no need to consider self weight additionally, it is inclusive of self weight. Into span is 6 divided by 8. So your M is equal to, the value of bending moment is, M is equal to, it is 90 kilonewton meter. This is the value of bending moment. So after the calculation of bending moment, we know the formula for the resultant stresses. So the resultant stresses can be calculated as P by A plus minus M by Z. Okay, so here you can see the resultant stresses can be calculated as P by A plus minus M by Z. Here we are not going to consider PE by Z, that is the stress due to eccentricity, because here we know eccentricity given is 0. So now after this we will put the values here in the formula and then we will calculate the answer. So now stress at top, we will call this as a sigma T, which is equal to P by A plus M by Z. So if I put all the values, P is 1200 into 10 raised to 3 divided by area is 24 into 10 raised to 4 plus M is 90 into 10 raised to 6 divided by Z is 24 into 10 raised to 6. If we solve this, we get the value of this bracket as 5 plus this is 3.75. So total stress at top sigma T is equal to 8.75 Newton per mm square. This is the stress at top. Now similarly stress at bottom. It can be calculated as P by A minus M by Z, which is equal to 5 minus 3.75, which is equal to 1.25. This is your sigma B, stress at bottom. We will call this as sigma B. So at top the stress is 8.75, at bottom the stress is 1.25. This is the calculation of the stress by using this stress concept. Now we will see the strength concept. So in the strength concept, now first we will calculate the shift of C line from P line. The shift of C line from P line, it is denoted by letter A. It is calculated as M upon P, which is equal to 90 into 10 raised to 6, that is the moment, divided by P is 1200 into 10 raised to 3, and this A is works out to be 75 mm. So now the resultant stresses in this method E can be calculated as resultant stresses is equal to, the formula is C by A, it is C by A plus minus C A dash by Z. So if we put the values over here in this formula, we will get the resultant stresses. So here the stress at top sigma T is equal to C by A plus C A dash by Z. This is the formula. So if we put the values in the formula, it will be 1200 into 10 raised to 3 divided by area, it is 24 into 10 raised to 4 plus again force into A. Here it is not A dash, it is A. A is 75, we have already calculated that value, and Z is 24 into 10 to the power 6. Now after solving this, we get this value as 5 and this value as 3.75. So stress at top sigma T is equal to again 8.75 MPa, Newton per mm square. And similarly stress at bottom sigma B is equal to C by A minus CA by Z. So C by A is 5 minus 3.75, which is equal to 1.25 megapascal. This is your stress at bottom. So here you can see by both the concepts, by stress concept as well as by the strength concept, we are getting the same answer. So in this way we can calculate the extreme stresses at the midspan section of the prestressed concrete beam. This indicate that when we consider the prestressed concrete beam, the cross section of the beam, at the topmost layer the stress is 8.75 MPa, and at the bottom level the stress is 1.25 MPa. That's it. Thank you.